Fine. Very good. Good morning, ladies and gentlemen. Let me start with today's lecture. And today we will quantize the classical fields we have studied in the previous lecture. As far as you remember, we've been talking about fields in general. Electromagnetic field was a particular example. Other example, which we just made up to show how universal is the concept of the field. We made, for instance, from balls connected by springs from a string. That we will also recall today. But the main message is how to quantize it. And eventually, after all preliminary work we did, when talking about classical fields, and the work we did is to describe each field in a universal fashion with the help of generalized momentum, generalized coordinate. Once we have done this, the quantization is a piece of cake. I will share this. Basically, just assigning hats to classical values, promoting them into operators. And we start with describing this procedure for harmonic oscillator first, for a single oscillator. Then, since we know that any field is a big set of oscillators, we will repeat this procedure for many independent oscillators. Right. We will talk about states of the fields. That would be more or less repetition, because we will recognize that states of the fields are equivalent to the states of bosonic particles. So Fock space number states will become a natural basis for our quantum field series. Then there will be rather diverse topics. How to keep track of this? First of all, well, we have quantized field, we have particles, and I will talk about particles, some properties of photons, electromagnetic fields, some properties of phonons, and which means mechanical oscillations. We will look at the string model again. In fact, the particles would seem rather similar. Then, important concept, important for understanding kind of the physical meaning of the quantization, is the concept of field operators. Field operator is expression of original field value, like electric field, magnetic field, or displacement in a string model. Expression of this in a universal language of creation and annihilation operators. That would allow us to write field operator, and with this we go for a set of interesting related topics that include zero-point energy, quantum fluctuations in an oscillator. Fields will become operators, and there can be uncertainty relations for the fields. And there are also non-zero values of field fluctuations in vacuum state. Vacuum fluctuations of the fields. All that we will cover today in the lecture. Fine. Again, I gave so much time to introduction because to outline, even short to say, to stress what are the main topics to learn, what are main things to bring home after the lecture. Let's go for details. Sure, harmonic oscillator. We have seen this in the course several times, but let me still repeat what I have. We will start with a simple model of harmonic oscillator, which is after rewriting everything in terms of generalized momentum, generalized coordinate would help for any oscillator. We will start with classical Hamiltonian describing this oscillation. From the classical Hamiltonian, we can derive the equations of motion. A peculiarity of the oscillator is that these equations of motion are linear equations. You remember this? I don't write it down explicitly because I have very important things to do. I want to describe you a quantization procedure. Quantization postulate. So how to go from classical quantities to quantum mechanics? One has to take into account the difference between definition of physical quantities in classical mechanics. There they are numbers, while in quantum mechanics, those are operators. So first thing which I have to do in course of quantization is to give heads to both operators, operator of momentum and operator of coordinate. Fine. That's an important step, but it's pretty void. Why is it true? Because we don't know how to operate with these operators. Or to put it precisely, we don't know how do they commute. We don't know commutation relations. And to tell you the truth, quantum mechanics just postulates these relations. After that, one can see how consistent it is. One can draw many examples showing that all possible quantum formulations of quantum mechanics are equivalent. But this is one of them, and this is a pure postulate. We postulate that the commutator of coordinate and momentum is just proportional to universal constant, to Planck constant. Right? Good. So now we know the commutation relations. Now we can go back and check the equations. Well, how we can do this? First, we could derive quantum equations. Quantum equations we derive, well, with the help of Heisenberg. As you remember, a derivative of arbitrary operator. What was that? Actually, I don't remember the sign. It's not important. I guess it's I. Commutator of H and A. I shall divide by H bar to keep good dimensionality. So that's the way to derive quantum equation for operators. Then one just compares with classical equations for numbers. And if there's a consistency, then it's fine. We reproduce everything correctly. We have built quantum mechanical description of harmonic oscillator. Fine. What I said is rather simple, but just check whether you kind of accept it, whether you can link it to quantum mechanics, you know already. Let me try to see chart. No, I still cannot see it properly. That worries me a bit. How can I? No, perhaps there's no way to see chart without actually stopping the windows, stopping window share that I don't want. And I don't see any messages in the chat. If there are any messages at this moment, please unmute yourself, speak up. I want to know this. All right. Otherwise, I will go with the lecture. Let's see. So we have quantized a single harmonic oscillator. Right. We have quantized it and we must proceed further. And there are different possibilities. One can, for instance, using commutation relations between coordinate and momentum, do Schrödinger equations. In coordinate representation, Q would be just become a number Q, and momentum would become and from that one can rewrite energy in the form of Schrödinger equation. There is a possibility, one knows that one can write Schrödinger equation for an oscillator, but that's not the way we proceed. We better proceed with operators. We talk about these operators. There's also ladder operators. They either reduce the number of excitations in the oscillator by one. Oh, now I see the chart. Interesting. It's a bit too many windows which Zoom produces. we talk about operator. This is operator which reduces the number of excitations in the oscillator. That creates an extra excitation. All right, they are made of operators of coordinate and momentum in a certain very fixed way. Good, so one can look at commutation rules for these operators, commutation relations, and they are like this. We have done so in the first lecture, but that time we don't have any interpretations for this. And now we got with an interpretation which, after all words said, looks pretty trivial for us. But it was really a great idea for physicists of that generation. The idea is that these commutation relations for oscillations for linear fields are just precisely the same as for bosonic particles. So, in fact, each oscillator can be described as a particle, as particles, which are there in a single level. Exciting oscillators, we just add number of particles into this oscillator. Reducing its energy, we just annihilate some particles in the oscillator state. That's kind of simple picture of quantization. Good. What I said, it's not, it should not really be new for you, but let me repeat, it's harmonic oscillator. We have quantized it, which means that we established the commutation relation between operators of coordinate and momentum. And we also made an appointment to treat harmonic oscillator with operators. And now we can give them proper names. Those are annihilation and creation operators of bosonic particles. Let me summarize it. Let me describe this oscillator as a level for bosons. Here on this slide, I have everything what one needs to make this oh, something wrong with my pen. To make this to get the essence of this. First of all, Hamiltonian. In terms of operators, it reduces to this quantity. Here, n is the number of particles, number of excitations in the oscillators. We see that particles in the oscillator do not interact. Why? Because their energy is just a sum of individual particle energies. What is interesting, important, and we will devote some time during this lecture, it's 1/2. There is some energy in the oscillator, even in the absence of any particles. Good. So what are eigenstates of the oscillator? They differ by the number of particles and they form equidistant spectrum. there is a special state of vacuum, ground state of the oscillator. It is defined as all vacuum we defined. It is the absence of any annihilation. Nothing can be annihilated in vacuum because there's nothing to annihilate. So if you apply an annihilation operator to vacuum, you got 0. All other states can be made from vacuum, starting from vacuum, by creating the number of particles needed. This is normalization factor. Eigenenergies of the oscillator, well, here it is. It's basically what I have here. N is quantized number of particles. Good, that was oscillator as a level of bosons. Fine. No serious questions. Let me try to see the chat again. It looks there's nothing in the chat, but again, I cannot really readily invoke the chat window. All right, let me go further. What I'm going to do now is basically to repeat everything which I said, starting from the beginning of the lecture, reformulate it for many oscillators. I just was lazy. I did it with copy and paste, adding something important. So let me concentrate on the important. We are talking now about big number of harmonic oscillators. They are independent. Fine. We can talk about particles in parabolic potentials, representing those. There's something bad with my pen. Fine. So the Hamiltonian would be just the sum of single oscillator Hamiltonians. Equations of motion we got from this Hamiltonians, they're still linear and they don't have cross terms. There are independent equations for each individual oscillator. Fine. Let us quantize those. So quantization is just giving heads to physical quantities, promoting them into operators. And we now have to fix the commutation relations between the operators. We fix it in this way. What is logic behind? Well, logic is very simple. The commutator is present only for the same indices for the same oscillator. And different oscillators, separators there, they are just commute because the oscillators are independent. Good. So what we did, we have quantized a large set of oscillators. And as earlier, we do this with operator algebra. Showing equation is a possibility, but we take it apart. So for each oscillator, we introduce annihilation and creation operator made from coordinate and momentum in a certain fashion. And well, that the commutation rules these operators obey. They can be derived from the commutation rules we have just recently postulated here in this transparency. Fine, so let me repeat it. Making it in plural form consistently. We can rewrite the total Hamiltonian in terms of these operators, and the result is just a sum over individual oscillators of the set. For each oscillator, we have individual number of particles in this particular oscillator, and k. And that characterizes an eigenstate of the oscillator, a basis state in Fock space. Right. We have a special state, vacuum state for this oscillator system now, which is, by the way, the direct product of oscillator vacuum. Each oscillator has a vacuum, and it's a direct product of this. Anyways, the definition is such that at any k, we cannot annihilate anything in this vacuum. That's enough. And all other states we can make from this. How do we do this? We create the number of excitations in each oscillator. Oscillators are labeled by k by implying creation operator, corresponding creation operator. Oh, I miss here k. Corresponding creation operators as many times as it is needed, namely nk times. Fine. That brings us to eigenenergies. Anyway, the oscillators are independent. Corresponding particles do not interact. So the energy is just a sum over single particle energies. 1/2 is their 0-point energy. We will talk about this. Good, oscillators as levels for bosons. That's basically completes the formal description of quantizations. So from now on, we know that any field, any classical field, in fact, is a field which can produce bosonic particles. And we can describe particles as a field with the help of field operators for particles. So now we come to, well, it's, you know that's why it's not really very much surprising. But this is some myth of our course. We have quantized particles, understood the properties of their fields. We have quantized fields. We have understood that there are particles behind each classical field. So we have a consistent picture whether particles and fields are not opposites, are just different facets of the same concept, the concept of quantum field. Fine, let's see how much time we are at. Okay, so there's still quite some time to go before the break. Let me Well, basically, I think I have already told everything which I have in this transparency. Let's look again. So any field is a large set of oscillators that I said. Quantum states of the fields, states of the oscillators. So we have completed second quantization. We did it into waves from classical particles to the fields. And there the most important step was to make operator of the field operator. Now we got from classical oscillators presenting field to creation annihilation operators of the particles. Here's there. Very good. Let me talk about field operators. Why do we talk about this? Why do we pay attention to this? Problem is that quantization is the same for all operators, for all examples, for all field series we just studied. And this quantization just expressed in terms of creation operator, annihilation operators, which are based certain commutation relations. But these operators originate from different fields. And in order to understand sorry. In order to understand the quantum properties of the fields, one needs to express these fields in terms of creation annihilation operators. We won't like to present classical field as a field operator. I hear some noise. Anybody tries to say something? What a pity that I don't see chat today. Perhaps, but I don't see anything which is printed in the chat. Again, if there are messages in the chat which I cannot see, please unmute yourself and tell me about this. Right. We need to for any classical field find a corresponding operator, one to mechanical field operator. But we have actually done this. Let me recall what we did when we were talking about classical fields. Any arbitrary field we can present in terms of normal coordinates, represent an oscillator field. These normal coordinates we can rewrite as generalized momentum and coordinate. And from this, we can go to operators. creation and annihilation operators. This is just a set of linear relations. What we want to do now is just to invert this set of linear relations. From creation and annihilation operators, we can express generalized momentum and coordinate. We can express normal coordinates, and those we can, from the normal coordinates, we can express the field. But now the field becomes an operator. That's how we introduce field operator. And let see. Let me just give an example of such field operator. To this end, we go back to one of the models we discussed in the previous lecture, the model of elastic string. And we will try to understand the quantized version of the string. String will oscillate. In quantum language, these oscillations will be quantized, will become particles. These particles, since they represent mechanical oscillations, are called phonons. They are characterized by momentum, which is made from wave vector. They are characterized by energy, which corresponds to the frequency of these oscillations, right? That's what, this is dispersion law for the frequency. Right? So we now call these excitations particles. That is not yet constructive before we actually established field operator. Here it is. So what I did, I took an expression for a normal coordinate, d, which we have derived in previous lecture, and call it a. And from that, I expressed back the displacement. So U of k is an oscillation amplitude in each oscillator mode of discrete k. Good. With this, I have the following. Now I have an operator of the field which depends on a point in one dimension and on time. And it expresses the field in terms of creation and annihilation operators. Here we find plane waves, wave functions of the excitations. And here we find, you know, this famously ugly square root, which had to be here to provide usual expression for normal coordinates, universal for all oscillations. So that's where all the physics goes to. This already bears information about parameters of the string, about its density, about its elasticity that comes in terms of frequencies. Fine. Right, sir. I want to say something important in this stage. This expression for a field is a linear function of annihilation and creation operators. That's what we expected from the very beginning. That's what we get. Let us recognize a simple consequence of this. Namely, if one takes expectation value of u for any number state, one gets 0. Why is it so? Well, let us take number state. Let us act on it with these operators. Whatever we do, we change occupation numbers in corresponding levels, either by +1 or -1. So the resulting state would never be the same, which means that these states are orthogonal and corresponding matrix element is 0. Right? So there are states, however, where this average is not 0, but those must be superpositions of the number states. Very good. So let me talk about electromagnetic fields as a collection of particles. That, I guess, you know from school days, or perhaps from preschool days, I don't know. Surely you have heard about photons. So the quantized excitations of electromagnetic field are called photons. Where do they live? What are the bases of quantum states of a photon? They live in the basis of wave vector and polarization. You remember polarization for each wave vector. We have two waves of two possible polarizations. And the whole state of electromagnetic field, one of its basis vectors, is a basis vector with certain numbers of photons in each state of this kind. So we have occupation number, which depends on quantized vector k, and two polarizations. The set of these numbers characterizes a quantum state of the field. Fine. A little bit about properties of the photons before we go to the break. Energy. As for any oscillator, it is a sum of photonic energies. Energy of each photon is h bar times omega. So it is proportional to wave vector. Momentum, one can associate it with a Poynting vector with an energy flux. From this, momentum is here. That's what we expected. H bar times wave vector. Checking it on consistency with relativistic rules, we conclude that energy is just speed of light times momentum. There is no rest mass for the photon. Photon cannot come at rest. That's what we know as well. Statistics, photons, bosons, well, just basically pure construction. We have quantized classical field. We couldn't get anything except bosons. No way. A little bit more about photons, about peculiarities said by photons. Some tricky thing. Kind of classical confusion comes when we talk about spin of the photon. I'm sorry. About photon spin. In fact, photon spin is 1. But it seemed to be in a contradiction with the fact that photons that we know have only 2 polarizations. For spin 1, one would normally expect 3 possible states with Z equals 0 or plus minus 1. But we see only 2 polarizations, and in fact they correspond to 2 spin components, Z plus minus 1, and in this case it's spin in the direction of the propagation, in the direction of photon momentum. The question is, where is the third component? The answer is that photons just rush too fast. They always go with speed of light. They cannot be stopped in our coordinate system. That's why that component is not available for us. It could have been different, or perhaps it will be different when we become, I put, it has to be photons. But that's my usual mistake. It also has some pedagogical value. I always mess up phonons and photons. Right. Photons just rush too fast, so we can never be in the same coordinate system as photons. That's why we don't see this third possibility. If you were photons, if we could move with speed of light, we could have seen that. Fine. Photon coordinate, for many reasons which I don't have time to discuss now, it is not a good idea. One can also get it from school days, from geometrical optics. When we talk about light, we always talk about light beam. And it is not really clear kind of whether we can localize light at each point of this beam. So it's better to think of photons as being spread at least in one space direction, having constant k in a certain direction rather than a certain coordinate. What I also wanted to say. There is a simple way to classify different particles, different fields, elementary fields, which come in our universe with respect to relativity principle. So there are fields, relativistic fields, which are massless, which don't have any mass. In this case, the classical limit is a limit of a field. Indeed, that's rather electromagnetic waves oscillations of different. If mass is not zero, then it's not field, it's rather matter. Rather, those are particles which can be rested, which can have momentum and coordinate. It's a classical limit of field theories for massless and massful particles. Right, I guess that's what I wanted to say before the break. So let's have traditional 8-minute break. Sure, we look at the photons. Again, it's photons, not phonons. I tend to mix them up. Edge particles, but I guess most of that you have remembered from school, perhaps, except the spin consideration. Photons move too fast. That's why we can see only 2 spin components from 3 spin components available. All right, let me talk about more constructive expression. Let me talk about correspondence between electromagnetic fields and annihilation and creation operators. Here I have only term with annihilation operators, but what I do, I have complex conjugation term of the same kind. I have to have it because this is complex conjugated operator, real quantity. And that complex conjugation part that contains a delta k alpha. Good. So what do we have here? We have here vector potential, and it's a sum of all possible modes, oscillator modes, and their polarizations. There is an ugly vector, and there are these operators accompanied by their wave functions, which are in this case plane waves, and also polarization vectors. Fine. Once again, operator of vector potential in a given point, given time, is expressed in terms of operators. I kind of retain their time dependence, but the time dependence is just trivial. It's a vector of I omega k t. And I have plane waves. I have polarization vectors. So we can express vector potential edge point through relation operators. What we can do with vector potential, we can do with fields. Well, because electromagnetic field is just proportional to time derivative of the vector potential. And the magnetic field is proportional to curl. Right. From these formulas, we can have field operators for electric field and for magnetic field. We found similar eigenvectors. That is how this algebra is reflected here. Vectors for electric field will contain polarization vectors. Magnetic field will contain polarization vectors, vector cross product with direction of propagation. Good, so we have established field operators for electromagnetic field. What for? What we are going to do now is to address, let me call it mysterious quantities. I don't think they could truly mysterious and very simple, and we crack it very soon. But as that concerns many simple things, there are many wild stories related to these quantities. Let me list the quantities we will talk about. We will talk about 0-point energy. We will talk about uncertainties between different field components, similar to uncertainties between momentum and coordinate and an oscillator. And we will also talk about vacuum fluctuations of the fields, non-zero averages of squares of these fields in a vacuum. Right. That's a standard illustration. It is sci-fi cosmic ship which utilizes 0-point energy accumulated in a vacuum to achieve the propulsion. If I look at it attentively, it must be faster than speed of light. It is a joke, of course. It's not even my joke. There are still people who are ultimately fascinated with this concept. When many years ago, when I just started preparing my course of advanced quantum mechanics, I wanted to get some material for next lectures. And surprisingly, I have found pretty good material at Wikipedia. Eventually, I'm rather critical about most Wikipedia material concerning physics. I can explain you why. Physics is very tight science. Different concepts are closely linked between each other. And actually, physics is not about each concept, each individual phenomenon. Physics is about links between different phenomena. Wikipedia mostly ignore this aspect because for Wikipedia, it is important to deliver a piece of reliable information about certain Wikipedia topic, right? And the links are not usually covered because it requires too much words, it requires too much energy from the authors, it requires too much qualification. That's how it works. And yeah, but that time I have found very excellent articles about basic concepts of advanced quantum mechanics, and I was astonished because apparently somebody with very high qualification just got enough time to do these tasks. I don't have such time. My colleagues don't have such time. And I tried to trace these people, and I have found the trace. It appears to be that in United States, California, there was a scientific institution privately funded with the sole purpose to study zero-point energy and find practical applications of those. All right. For me, this task is impossible. And I guess after my course, you would also agree with me. But anyway, it's private funding. They could do something about advanced quantum mechanics. They could at least write good articles in Wikipedia about this. So there are mysterious quantities. Let me talk about this. 0-point energy. Fine, we flash again this Hamiltonian. It is Hamiltonian of electromagnetic field for this particular basis, but it's valid for any field. There is some energy in this field, even in the absence of any excitations, in the absence of any photons. Right. The energy is a good question, very practical and instructive question if we can use it. Well, we could, but for this, we would need to have to change the vacuum. We would have to change the properties of the vacuum, and namely this oscillator oscillation frequencies. If you do this, we can. Normally, we cannot. So this energy remains intact. But anyway, it's like, you know, counting money in somebody else's pocket, trying to figure out how much does your neighbor earns, right? You can also do similar calculation. Let us understand how much energy is there in a vacuum. Take an electromagnetic field as an example. Well, let's make a sum. That sum is, of course, kind of infinite because of infinite number of terms. Let us understand how infinite is infinite. First, we will transform the sum into the integral, so we will understand that it will be infinite because the volume is infinite. Well, we can divide on the volume, we can get finite energy density, energy per element of volume. But what stands here is also infinity, namely it diverges at decay. This integral diverges at large k, or one can say at large frequencies. Here I just written it in terms of frequencies. Recalling the formula we have derived, how many oscillators are there in an frequency interval of delta omega. In any ways, it's also density of energy density which diverges, which is infinite. Right? And good. If we don't think of, if we don't trace all possible links between non-physics, that's in principle fine. We have some energy, but we cannot get gas on it because we cannot change the properties of the vacuum. So let it stay. The problem, and well, despite the fact that physics has many advances, this problem is not yet solved. The problem is, how do we survive in the presence of zero-point energy? Why is it so? According to general relativity, any energy is a mass, and each mass produces gravitational field. So zero-point energy would produce gravitational field, and that would be eventually enormous. It would diverge and would eventually collapse all of us. So it looks like zero-point fluctuations do not produce gravitational field as they should. Nobody knows why. Nobody knows precisely why is it so. There are theories that eventually there is positive contribution to zero-point energy from bosons and negative contribution to zero-point energy from fermionic modes. And if you have equilibrium between, if you have precisely the same number of fermionic and bosonic modes, then the resulting zero-point energy would be zero in the limit of big energies. This property is called supersymmetry, symmetry between bosons and fermions. Well, that explains why this energy doesn't go to infinity. There is a cutoff. There is some typical energy at which fermions and bosons become symmetric, pretty high energy, which would set some cutoff in this integral. But still, there will be some finite density of zero-point energy which would have produced gravitational field, and it doesn't seem to produce it. So nobody understands this fact. I'm sorry, I got to the wrong direction. Nobody understands this fact in sufficient details. But well, somehow we don't feel gravitational field produced by zero-point energy. Anyway, it's about very fundamental properties of universe. Let us better turn to something which we know in more detail. Let me turn to the work at energy scale of solid state phenomena. The message is, well, it looks very defined. but in fact it's a true message. We can change vacuum at this energy scale. How? Well, say simplest way, instead of vacuum, we put some crystal with the electric constant, epsilon r. And then all light modes in this new vacuum will have different velocity, which means that we have different 0-point energy corresponding to this modes. So we can compute the difference of the energy upon changing vacuum. Right? Here's the formula. I'll get it. Did I get it? I took this one. I got it, put in some critical value of frequency. So I get frequency to the power 4. And I put this change, I put this change of C in front of the integral. Here it is. That's how much of, right, so it's energy density to start with. That's how much energy per volume I can store in quantum fluctuations. What do I set for, what I need to set for this critical, yeah, I have it here, for critical frequency. Since this modification comes about the interaction of light with atoms, that frequency must be something coming from atomic energy scale, which we'd call Rydberg's. Well, one can express it in terms of electron charge and Bohr radius, atomic radius, a typical atomic radius. There's a formula for this atomic radius. Right, and what I want to do is to do the following. I would like to compute this energy change at the scale of atom. So I substitute atomic volume here. And the resulting expression, I would like to compare with atomic energy by itself, right? That, for instance, gives me an energy of an atom, and that gives me energy corresponding to 0-point energy at the same scale, at the same volume. All right. So I did this estimation, what I obtained. There is a factor between these two. So 0-point energy is much smaller than atomic energy. And there is a factor of, yeah, strange combination of elementary constants to the power 3. This is first time in our course we see here celebrated fine structure constant, which has a special, very profound name, alpha. And this fine structure constant is dimensions quantity which appears to be small, like 10 to the minus 2. All our words, as we will see from many examples in this course, is just made about the fact that alpha is small. And we see that this also sets the difference of scales between 0-point energy and atomic energy. At atomic scale, we have such a factor, so it's about 1 million 0-point energy is like 1 million times less important than usual atomic energy coming from interaction of protons and electrons and the kinetic energies. Fine, that was the estimation. So we have started with infinitely big 0-point energy. But we understand that for us, for persons who can work at atomic scale, the energy is in fact small. 1 million times less important than energies comprising atomic scale. Fine. Let me talk about uncertainty relations. Let me talk about uncertainty relations. Let me first describe those in general. Let me talk about uncertainty relation for something that you know, for momentum and coordinate. Uncertainty relation comes about from the fact that two operators cannot have common eigenvalues, common eigenfunctions, so that they don't commute. So from the fact that there's a commutation relation between momentum and coordinate, it follows uncertainties of momentum and coordinate, the product is always bigger, or at least of the order of h bar. That allows us to generalize these uncertainty relations for any operators, and in particular, we would take field operators. In this case, I don't want to specify the field. I only want to know that those are operators which are linear in creation, in annihilation creation operators with some coefficients, right? So I want to get generally the commutator of these two, right? I don't have to think much. I can directly calculate it. It is similar to calculations we did during problem solving sessions, during presentations. Let us see, what do we do? Well, we just plainly substitute all that. What we have is a sum over all modes and corresponding commutators. And we know what commutators are. For this case, this is delta KL honest, I believe, right? That will give us general formula for commutator of two operators, so we know the uncertainty. We can immediately jump to here. All right. So we also need something else, which I also want to treat in general. It's again the simple exercise calculation of the same level. Now I take two operators x and y, and I would like to find their fluctuation or correlation, whatever you call it. For classical variables, it would correspond to correlation like this. For quantum variables, we need to care about the order of two operators x and y. So let me put it into symmetric order. And that's what I want to compute, the anti-commutator of x and y. How do I do this? Again, first I substitute expressions for x and y, and I have to deal with a particular let's see, let's do this. Is particular commutators, sorry, anti-commutators of two operators. Anyway, for vacuum state, not for arbitrary state. For arbitrary state, it would depend on on number of particles, but for vacuum state, one can show that it is not zero only for k equals L. Right, that's how we come to this formula. For the fluctuation. Or one can reduce it simpler for the same operator. So the total fluctuation is a sum of particular fluctuations for each oscillator. Simple to remember. Good. I didn't want to specify, to do it, to run a specific calculation for any field, for any specific field, for electromagnetic field or for mechanical oscillations of string. I would like to derive a general. Then we can apply it to any situation we want, as far as we know this x and y, as far as we know specific forms of field operators. Good. So, as an example, we will look at uncertainty relations for electromagnetic fields. Let's take as an example, magnetic and electric fields. Uncertainty, we can use the formulas which we obtained in the previous slide. And, you know, field operators, where did I have it? Let me find it. Ah, here we are. We have field operators for electric and magnetic field. We can combine those two. To counter this. That looks like a terrible mess because, first of all, it should have been simple. Should contain only fundamental constant, that's fine. But there's so much case, so much errors. I don't really know how to compact it immediately. After looking at this attentively, after making all these limits, one comes to the following. Again, it's for specific component x and y. That's how uncertainty looks like. It means if the points here and here are different, the uncertainty is zero. They would commute perfectly. But if they're on the same point, the uncertainty would blow up, but it also doesn't blow up as a delta function. It blows up as a derivative of delta function. So if I would plot this quantity versus derivatives of that to this point, I would get something like derivative of delta function, something that ugly. Sure, it's not really very constructive, I would say. I don't know how to understand this delta function. There's a way to know this. It's the following. It is in high terms, it's called a spatial regularization. We regularize our space. We take our space. We separate it into cells of the size delta L in all dimensions. And in each cell, we kind of average over magnetic field over electric field. Thereby, we exclude fluctuations of the fields with very big wavelengths. Sorry, with very short wavelengths, shorter than this delta L. Good. Let's do this. Then we can finally get something interesting for uncertainty. So it scales like this. In this case, the uncertainty is only for B and E in the same cell. In different cells, those commute. Right, and one can see the following, that if one looks at the field at smaller and smaller scale, this uncertainty blows up. Sure. Never look at the fields at very small scale. It can become blurry. Let's do the same for vacuum fluctuations. Vacuum fluctuations of electromagnetic fields. We can do again, we can adjust general calculation I did for particular case of electric field. Right, what we get, then for each K we have well, just product, scalar product of polarization vectors. We can transform to integration of a quasi-momentum. In this case, we understand that we need to impose a regularization. We need to impose the highest momentum till which you can integrate. This highest momentum, let's call it critical momentum, would be of the order of inverse delta L, the size of the self we introduce in spatial regularization. Good. So the fluctuation of the field would have the same scaling as uncertainty of the field we studied. It would be like delta L to the power 4. Well, similar calculation we can do for magnetic field. And that's we do. And the calculations are very similar because, in fact, magnetic field and electric field are very similar quantities. Relation to 0-point energy. Did I put it explicitly? I just don't remember. No, I did not. Let me explain it now. There is energy of electromagnetic field, the energy density, which I believe we called U. And that was proportional to E squared. And it was also has a term proportional to B squared. Like there's energy accumulated capacitor, energy accumulated in inductance, those are these terms. Good. Then fluctuations of the fields in vacuum also immediately implies some energy density, and this is in fact 0-point energy, 0-point energy of corresponding fluctuations. Eventually one can find the correspondence between 0-point energy and these fluctuations. Fine. Let us now try to understand if these fluctuations are really infinite, and okay, they would be infinite only if we could compare it with some other case, which is something which we know, which we can compare with. So for this, let us do some estimation. Very instructive. So usually kind of nature is merciful, and we do some simple estimations disregarding many details of physical phenomena and still get something sensible. This won't be the case. Let me warn you from very beginning, but let me still do it. It's a lot of fun. Good. That is to figure out what would be fluctuating 0-point vacuum fluctuations of electric field as compared with the electric field at atomic scale. How do we do this? Well, we take what we have derived. This gives you vacuum fluctuations at space scale, delta L. And we substitute atomic scale. So eventually we replace delta L with Bohr radius. That's how much we got. And we can compare it with the scale of electric field in the atom. Right? That's something which electron experiences in from a proton. Yeah, apparently it is just the same Bohr radius which enters here. So electric field is electric charge divided by r squared being the distance. R squared is, R is of the rotary Bohr radius, that's how we get it. Now let us find the ratio between these two. Okay, we can do this algebra. This is proportional to power of AB. This is as well, so they should cancel. Somehow we have something which don't depend on Bohr radius. And we encounter our Euler quantities alpha. The only point, it's 1 over alpha. So we find that vacuum fluctuations of electromagnetic field at atomic scale is about 100 times more important than the field coming from the proton. Well, that must be very confusing for electron in the atom, right? If this calculation were correct, it would have to feel all this noise from vacuum fluctuations, and it would be impossible for electron to concentrate on the field of the proton. Good, so something goes wrong in this calculation. And let me, in the end of this lecture, I still have, I could do it within a minute. Let me explain what went wrong. We have made the answer, and it was a good attempt. We did it for instant fluctuations. Fluctuations at the same time. And we look at certain wavelengths. Wavelengths which is of the order of atomic scale. But the field at this length scale oscillates with enormous frequency, which is much, much bigger than typical frequency scale for atomic motion. That's why this field, which is present, makes no influence on electron motion. It oscillates too fast. So after taking that into account, after taking only those energies, frequencies of the oscillators, which are of the order of atomic energy, we kind of come back to the previous estimation which we get for 0-point energy. And estimation is that 0-point fluctuations, vacuum fluctuations, or 0-point motion, doesn't matter much, is 1,000,000 times less important than usual energies which particles experience at atomic scale. Good. That was estimation of vacuum fluctuations for electromagnetic field. I've also simple calculation for an individual oscillator, but I don't want to talk about this now. It's very much transparent. It's yet another application of general formulas I have to. Very good, sir. Let me conclude this lecture. Just, I would like to have some final response from those who are left. Was it okay with sound, with presentation, with everything? It's also sure that this is the last lecture before the semester break. We won't see each other even online for about a month. I guess I will want to make a survey to understand how we can get, let me put it like this, get closer, get more intense online education in the rest of the semester. I hope you will look at announcements and answer this survey. Is this? Bye. You can always contact me by email. See you soon.